Okay, so how's everyone doing? Nice to meet you. My name is Asaf. I'm going to present the work we did, Philip Shilane, Sarai, Sheinvald, and Gala Yadgar, my advisor, and I. My advisor told me to make a presentation for 25 minutes. I told her I need 3 hours, and she said that's not how it works. So let's get to it. All right, so I'm going to talk about deduplication. Deduplication is a method that we use to identify duplicates in data, mostly in backup systems and secondary systems, but today more and more also in primary storage. And it's everywhere in many storage products, many data centers. Let's say that the essence of this idea is that, let's say, a couple of files, maybe multiple versions of the same file, or copies that were modified, or files that share certain content. So files are made of blocks inside the disk, the storage, and whenever they share a block that is identical, they will point to the same block instead of having separate blocks for each other. So that's the duplication. It is composed of several parts. I'm gonna simplify that, but it's mostly, say, the files themselves. They have their recipes. That's how they're constructed. It's gonna be multiple chunks that each file contains. How the chunks are identified is by fingerprints. That's a hash of the content of the chunk. That's how the duplicated systems are built. So when I want to read a file, it's going to be restoring the file from the duplicated system, which means that it can be in random access because the chunks are stored somewhere on disk, and it might be something like that. Say I want to read F3, so it might be something like that. It's going to be a non-sequential order, and that would be deduplication. All right, so we got deduplication, and now I'm going to talk about keyword indexing. So keyword indexing, in its essence, is an external data structure that we use in storage systems to be able to look up several terms and query it. Say we want to search a word or a sentence or a phrase or some pattern. So we use a keyword index for that. And it is completely external to the storage system usually. And it has the abstract concept of documents, which means that we have a key value stored, that we have the field, which may be the content of the file or some metadata. And we would be able to search over that content. The content might be saved in the index or not saved. It supports that. All right. And it also supports advanced options. So when you look up a term, it might point to which file contains it, but maybe where it appears in the file, or maybe it would say how relevant is the result that it yields. And it's used in many contexts. It can be used in searching in large data sets, or it's also used for pattern matching, data mining, and natural language processing. I said it already, that many fields can be indexed and searched. Right, so let's get to our work. We tried to integrate indexing into the duplicated systems. So what would you do when you would try to index the duplicated system? So if you'd go to the problem straightforward, you'd probably try to read all the files by the recipes and restore all the files, and you'd have the deduplication-oblivious index, which means that what you're trying to do is read all the files, and you'd probably index duplicates as many times as they appear. You're gonna read the files, you're gonna read the duplicates, you're gonna go over the data in random order, and you're not even gonna be aware of that there are duplicates in the data. All right, and the index size is going to grow with the duplicates, which means that if we have the same term repeated many times or the same chunk repeated many times, then we're not going to benefit from the deduplication when we index that. So that's a problem that we try to address. But in this data structure, what happens is that search is pretty straightforward. I mean, it's just like keyword indexes that look like that, because you have terms and they point to the file that contains them. So it's a very simple data structure, and we can use it very quickly. So it's straightforward, but we want to introduce a different approach for that. So instead of indexing the files and restoring them and doing that oblivious, the deduplication-oblivious approach, we wanted to be able to point to the chunks directly instead of the files. So I explained the concept of documents, where we would index the files as they were documents. We would have we would have the files read, their content is going to be indexed, and now we say, all right, let's scrape that. Let's try to index the chunks themselves, the physical data, and not the logical data. So that's what we did. So essentially, what it means is that we created indexes for the chunks. Each chunk is as if it was a file, and then we treat the physical data instead. It sounds pretty straightforward, but it was not that simple. What we did is that first, when we tried to do that, we encountered the first problem where we split the files into chunks, into blocks. So no one guarantees us that the chunk is going to be split on a whole word. It may be split in the middle of a word. For example, in this case, the word the is split into t and he. So we're going to index words that don't even exist in the files. And that's a problem that we needed to address during our work. Another problem is that what we proposed indexes the chunks, not the files. So if someone's gonna search our index and receive which chunks contain it, then we did nothing, right? Because it's not a result. Nobody cares in which chunk the term appears. So we need to find which files contain a chunk when we index the chunk. So we need some kind of map, some kind of way to be able to invert that direction. So we need to go through the file recipes and realize which chunk is contained in which file. So it requires to create a data structure, and if a chunk is added to the system, it needs to be consistent. What if a file is deleted, and so on and so on. So that's another challenge that we had. And we add another level of indirection to the search, which makes everything more complex, more complicated, which means that we need to be able to create a new indexing method and new data structures and having a new lookup algorithm. And also, I said that there are advanced features in the index in the traditional system, so we will try to support that too. We want to be able to give scores of relevance to the results, which is now much harder because we don't have the original context of the data. And of course, showing the context in which the word appears, it's also important. For example, when you search something on Google or something like that, you see the context in which the result appeared, and we want to be able to supply that in our system. So it's going to be much harder with another level of indirection. All right, so the first challenge that we addressed is the fact that words may be split. We used a technique that we called white space aligned chunking. It is a technique that we used that we took the chunking method, the original chunking method, and we modified it so that the chunks would end always on a whole word. So we do something like that, where we would tell it, instead of chunking, instead of splitting the chunk in the middle of a word, to continue until the next white space. We did that, and then we fixed the map. So we experimented with that. We made sure that that it didn't affect the system. It was very negligible, and that's why we went ahead and continued with our work after we modified the chunking method. So that's how we did that. And how we created the index was like that. I mean, say we have a deduplicated system like that. So we're going to build first the physical chunk index. As we said, we're going to treat the chunks as the documents, and the index is going to look like that. We'll have the terms, and then we'll go over the chunks and create the map from the terms to the chunks, just like that, and so on. And what is important to understand here is that the chunks are treated completely as documents, which means that we treat the chunks as a file system itself, and we can use a completely traditional index engine for the chunks. We don't need to invent the wheel here in order to be able to index the chunks. All right, and then we need to invert the file recipes. So we just built a key value store to map from chunk identifiers to their containing files. So we went over the recipes and inverted the pointers, and we saved that in an external data structure too. So this part we had no magic solution to. We had to implement it ourselves and to find the right data structures to use. And after experimenting with a couple, we understood what's best, and we chose it. The good thing is that it is orthogonal to whatever data structure we would want to use. It's just essentially a key value store. So that was good for us, right? So now when we want to perform a lookup, which is the important part of an index, you build the index once so that you can you would be able to look up as many times you want. You're gonna just follow the maps, follow the pointers in order to perform a lookup. The chunk index would be some traditional index software that I'd send a query to, and it would return the relevant chunks. And then I'd have to look up the chunks in the map that we built in order to find the relevant files. So it would go something like that. I'd have the pointers traversed, and I would find the chunk, and afterwards the relevant file. So that's how we created the lookup. All right. So that was all a great idea presented. That we thought that, all right, it would be fairly simple and it would be straightforward, but then we went ahead and tried to implement it. We used Dester, that's the deduplicated system, an open source one from FAST15. Maybe soon will be the test of time candidate. We wanted to add an indexing feature to Dester, so we used Lucene. Lucene is a very prevalent indexing engine. It's used in Elasticsearch, used in Amazon OpenSearch, and many other search engines. We used an open source port of that, and we tried to integrate it into Dester. All right, so the Lucene data structure is simply a map from terms to document IDs. As I mentioned, documents are some field to value map, and it's gonna have its term to document ID store, where it's gonna when you send a query, return the relevant document IDs, and then you have the document store where you're gonna store information about the documents by their IDs. So in our naive approach, the approach that's the deduplication-oblivious, what we did is that we had a map from the document IDs to their paths, and that's how we would look up the documents, the relevant files. And in our deduplication-aware index, what we did is that we said that we would use the traditional indexing software to index the chunks, and that's exactly what we did. Now the documents are chunks, so the terms point to document IDs which represent chunks, and then we would have in the document store each document ID contain the relevant file IDs, and that's the chunk to file map. So that part is implemented inside Lucine's data structures, but we modified the chunking method to work for the deduplication-aware index. And we also added another key value store that would map file IDs to file names, so that when a chunk points to a file, it will point to a file ID and not a file name, and that would save a lot of disk space, because the file path is going to appear once and not multiple times for each chunk that is contained in it. And we stored that path store on an SSD. It was fairly small. It was just the file names, and we used that. We used that it is small to be able to store it on SSDs. And that's the base implementation, the core implementation of the system. But we also wanted to implement advanced features, because traditional index systems have advanced features, and we thought that if we can't have the same extendability that index software has, then what exactly are we doing? So we implemented something called inline indexing, which means that whenever you create a backup, whenever you duplicate files, you want to be able to index that while it happens. So we modified the backup process to be able to index that during the backup, and it was fairly interesting. We also added support for context for storing offsets, which required to modify both the Lucene index to index the relevant data and our chunk to file map, and the ranking to similarly. The details are in the paper. That's a more complex implementation that I'm not going to go into. All right, so we're going towards the evaluation. How did we evaluate the system? So keyword indexing is textual. We used textual data sets, a couple of Linux versions, and Wikipedia backups, which we split into files because the Wikipedia backups are very, very large. So we split them into files of 1 megabyte each. And we also made sure that there were a lot of versions of the data sets, varying file sizes and varying the duplication ratios. When we tried to test our index creation, that's what happened. We had a great reduction in indexing time. So our idea to be able to scan the chunks sequentially from disk and create an index from them was very useful, and it is deduplication aware, so each chunk is indexed only once instead of multiple times due to the duplication. So we got 78% of reduction in indexing time for the Linux data set. And we also reduced the index size. The idea behind reducing the index size is, of course, instead of pointing to multiple files containing the same term, we would point to a single chunk, and that chunk would point to the files that contain it. So that's the reduction in index size. But we got 56% reduction in the Linux dataset. But the index size introduced an interesting fact that we found out during research. It wasn't as straightforward as we expected. What happened is that sometimes the index got very large, and the fact that we saved information per chunk introduced some trade-off. So what was the trade-off? We always said that if a term appears in multiple files, which is in only one chunk, then we would point to that single chunk, and we would deduplicate the pointers in the oblivious, deduplication-oblivious index. But there is another case where pointing to the chunks instead of the files actually increases the index size. So in a case, a term points to a file, but this file is very large. It contains many chunks, and this term appears many times in that file. So what would happen is that this term is going to point to multiple chunks that it appears in, and each of these chunks are going to point to the file. So in a case where files are very large, what's going to happen is that we're going to multiply the number of pointers in the system, both in the term-to-chunk map and the chunk-to-file map, which would result in a much larger index, and that's a trade-off that was introduced by our idea. All right. So I'm going to go over to the lookup times. All right, so I'm showing here results for both light and heavy queries. So I'll just define what a query is. Sending a query in our experiments was simply a set of keywords in an OR manner. If the file contains any of these keywords, then return the file or the chunk. And we achieved a major reduction in lookup time. So the reason that we achieved that was a much smaller index and fewer redundant results. I mean, when we looked up the index, we would much less chunks were returned instead of the amount of files. And then in the chunk to file map, we just had less lookups. So for example, if I had n terms in m files, so the duplication would make it n plus m pointers traversed instead of n times m for the duplication of many chunks in many files. Right. So the frequency of keywords also affected the time. So what happened is that for the lighter queries, there was a bigger benefit, and for the heavier queries where the terms appeared many times, it was the case where a file contains the terms many times, and it was exactly that diamond-like diagram that we saw earlier, and that's the cases where the lookup times were a tad less beneficial. All right. And we still got a great reduction in both cases. All right. So in the paper, we have a much more detailed experiments with many types of queries and different number of keywords. Right. So more results about the advanced features that I didn't go into in detail. The inline indexing, we were able to implement inline indexing and to reduce slowdown very well. Also, we implemented offsets. We supported offsets, and we were able to show the context in which the term appears. And in this case, when we stored offsets, the naive approach didn't have the diamond advantage anymore, because it needed to store for each term's appearance where the offset in which it appears. So having the term appeared multiple times actually increased both the index size and the lookup times. And we also supported ranking mostly as a proof of concept, and we wanted to show that it is expandable, and we did. There was a benefit from our approach there, but there's more work to be done there. The details, of course, are in the paper. So to conclude, we can support full content indexing. So until now, we didn't find much work about full content indexing in the duplicating storage systems, and that's what we did. Our approach had benefits, and that was the work. We were able to improve upon the naive approach, and we were able to implement the features that we wanted to implement in order to prove that it is also extendable and not only functional. And in future work, we're gonna try to implement more complex queries and maybe supporting non-textual files such as PDFs or Word documents, and that's it. Our code is online, and we also have the way to reproduce the results. Thank you very much for your time.